Now let us consider two more molecules and write down the structural fingerprints for them as well and see if we have any challenges associated with it. So we are now going to use the same keys that we used last time, and again let me just make the table like this. So I'll have the keys and the values. Once again I am creating a vector type of description. So key 1, 2, 3, 4, 5, 6 and 7, and then let's continue over here. So I have got 8, 9, 10, 11, 12, 13 and 14. Now over here we see that aromatic rings are present, so I'm going to put one here. And for the second molecule also the aromatic ring is present, so I'm going to put another one. Then again, for this molecule, do I have a benzene group? Yes, I do have a benzene group. I have the benzene group here as well, so I'm going to put one over here and so on and so forth. So same thing, I have an aliphatic chain present, so I'm going to put ones over here. I do not have any of this ether, epoxies and so on, so I keep on putting the zeros, and the zeros are for both. And again, if I keep on doing that, once I get to an ortho substitution, I see that over here I do have an ortho substitution, so that becomes 1. This is not, if you look at these two positions, it clearly tells me that I've got an ortho substitution, but I do not have a para substitution. So I'm going to put zeros in over here. And then do I have methyl groups? Yes, I do have methyl groups, and I do have second methyl groups and so on and so forth. So I start putting the values over here. And so then what happens is I end up having two molecules which are actually different, but then even though these molecules are different, they do not really have different representation when I look at the structural fingerprints. So this is one of the challenges with structural fingerprints. You can get into a situation where two different molecules end up having the same type of structural fingerprints, and you are not able to differentiate between them. So this is actually a real problem. So when we have problems like this is where we need to come up with a different type of fingerprinting method, and the structural fingerprints no longer work. And so that is where we get into something called the topological fingerprints, which are part. If we use the structural fingerprints as we did just now, what you will see is these keys are actually identical, and there has to be some way in which we will be able to differentiate them. So the challenge with the structural key fingerprints was the fact that sometimes two entirely different molecules would end up having the same fingerprint. And in order to circumvent those type of problems, people came up with other type of fingerprinting methods. And this is where the topological or path-based fingerprints came into the picture. Now, the idea behind the topological fingerprints is that it is going to encode the 2D connectivity of the molecule. This is not something which is very well suited for looking at the 3D type of representation for molecules. So for that, you have got a separate type of fingerprints like the 3D fingerprints. But by and large, this is going to encode the 2D connectivity of the molecule. And this is really where we again go back to our concepts of graph, and we start considering this entire molecule as a graph. And so when we consider the entire molecule as a graph, the atoms are considered as the nodes, and the bonds between the atoms, those are considered at the edges. And then what we also say is that the paths are going to be hashed into a fixed binary vector. So as we say that, we are basically introducing a couple of new terms. So the first term is what we call a path. So what exactly is a path? A path is nothing but a sequence of connected atoms. So if you have a molecule, you will have a bunch of atoms which are connected to each other. So for example, if I take something like a benzene, right? So a benzene molecule is going to have a bunch of carbon atoms which are going to be connected to each other by a very specific type of bonds. So if I start going around the molecule, starting from the first atom to the next atom to the next atom, so I now start tracing out a path. So this connection between the atoms is basically what we term as a path. Now, if you are looking at really long molecules, the number of paths will become very large very quickly. Some of these molecules might be having hundreds of carbon atoms, long chain polymers and all. The number of paths would be really increasing really exponentially. So what do we do in such a case? What we do is we arbitrarily set some sort of a limit as far as the path length is concerned. And this actually makes sense because the influence of the nearest atom is going to be a lot more on your reference atom than the second nearest, and that would be more than the third nearest, and so on and so forth. So as you go further away, the influence of the neighbor, like the 7th nearest or 8th nearest or the nth nearest neighbor on your reference molecule, is actually going to be relatively less. And so by convention, we consider path lengths somewhere between 2 to 7 atoms, not more than that. And that is something which allows us to keep the number of paths to some sort of a manageable limit. Now, of course, this 2 to 7 is not a hard and fast rule. You can have maybe a path length of 8 atoms or 9 atoms. Nothing stops you from doing that. But as a convention, we usually pick somewhere between 2 to 7 atoms. So in addition to paths, the other term that we introduced is what we call the hash. So hash function is basically a mathematical function. So when we say that paths are hashed into a fixed length binary vector, what we really mean is the string that represents the path becomes the input for a hash function. And this hash function is basically a mathematical function which is going to take a string or a number or a data structure as an input, depending on how you are representing the path of the molecule. And then that function is going to transform that input into a output which is basically going to be an integer. And this is a fixed size output. This is a very deterministic function. It's not a stochastic function. So once you define a hash function, the hash function should be defined such that when you give one input, it is always going to provide the same output. Okay, you do not encode any randomness in this. It is going to be a deterministic function. So how you are able to generate a hash function, that is another line of research by themselves, but let's just give you a very simple example of a hash function. So let's say the hash function is denoted by h of x. So I could have something like h of x is equal to ax plus b. The entire thing is then modulo of some other number n. So here a and b could be integers, x would be your argument, and n would be, let us say, a prime number. It's just an example that I'm giving. Many times what happens is people actually try and break down the string values of your input functions into the corresponding ASCII codes of those alphanumeric terms, and then those ASCII codes get added, and then it's a modulo of some sort of a prime number, and then whatever remainder you get, that is the hash output. So that is how the hash function works. Now at this stage in this lecture, we are not really going to get too deep into the hash functions themselves, but the basic idea I want to convey is that in case of hash functions, you can take an input which is essentially a string that represents the paths in a molecule, and then that hash function is going to give you a unique numeric output. So you can use this type of function in order to map molecular paths or substructures to positions in a fingerprint vector. And this part is really important. You are mapping the substructures to the positions. When you were using the structural keys, all you were doing was identifying the substructures. So you could be having the same type of substructures, but then if they are occurring at different position, the structural keys will not be a very good way of resolving them, and that is where this type of topological path functions, where the paths get hashed onto the structure vector that you are building, comes into the play. And this is really a key improvement of this type of fingerprint over the very simplified structural key based type of fingerprinting methods. So by and large, when you are using a topological fingerprint method, you are trying to capture the branching and all of the subtle differences in the connectivity which the structural fingerprints can sometimes miss. Now let us go back to the two examples that we were looking at when we were looking at this structural key fingerprints, where the fingerprints did not differentiate between these two molecules. So 1,2-dimethyl-benzene, 1,2-diethyl-benzene. So of course one could actually start encoding more structural keys in order to differentiate them. That can always be done, but then if you remember, the number of bits in the different types of formalism were actually restricted. So Max had a certain number of bits, PubChem had a certain number of bits, and so on. So you would, in case of large molecules, very quickly get to some sort of a limitation in terms of the number of bits, and so there would be only certain types of substructures that you can encode. And once you get into that type of an issue, you have this problem where just the existence of the substructure would not be sufficient to differentiate between two different molecules. What really is happening over here, if you look at the first case and then you look at the path, your path over here and the path over here is simply terminating. So you simply have a carbon-carbon where this carbon is belonging to this benzene ring, and then the other carbon is essentially due to a methyl group. So you have a path which is terminated. So we can say that we have a situation where the path is terminated at the first nearest neighbor carbon from the benzene ring. If you look at the other molecule, the path gets modified a little bit, as in here and as in here. So now you still have the carbon belonging to the benzene ring, but then you now start having a little bit longer path. So in this case, the path is getting terminated, but not at the first nearest neighbor carbon, rather the second nearest neighbor carbon from the benzene ring. So if you are able to identify these different paths in the molecule, you will be able to differentiate them based on their topological or path-based fingerprints. The third type of fingerprints that we are actually going to consider are what we call the circular fingerprints. And as discussed earlier, the circular fingerprints, this also works almost like this nearest neighbor type of approach, where you have to specify a certain radius and then you start looking at the relationship of the different atoms with the reference atom, which is at the center of this circular region which you are looking at, or the circular neighborhood which you are looking at. So let us take an example with a very simple molecule so that we can understand this concept of circular fingerprints a little bit better. So let's take the example of something as simple as ethanol. So if you look at ethanol, let us initially start with what atoms are there and what their identifiers are. So here we will continue with the practice of not really mentioning the hydrogen atoms. We will simply talk about all of the other elements which are present. And then the assumption, of course, is in order to fulfill the bonds, the balance would come from hydrogen. So we have a carbon atom over here, which is connected to 3 hydrogens, and then we have a second carbon which is connected to a first carbon and an oxygen, and then of course it is connected to 2 hydrogens, and then you have got the hydroxyl which is coming at the end, and that is connected to 1 hydrogen, and on the other side it is connected to the other carbon. So what we have is a initial identifier and all of the atoms in the molecule chain. After that, what we do is we start with zeroth iteration, and zeroth iteration means we are looking at a radius of 0, which means we are looking at the individual atoms themselves. So here what we say is at 0 iteration, the first carbon, I am going to call that as a degree 1 carbon, and I call it a degree 1 carbon simply because it is connected to only one other carbon. The second one, I call that as a degree 2 carbon, because unlike the first one, which is connected only on one side to a carbon, rest is hydrogen and we are not considering the hydrogen, the second carbon is actually connected to a carbon on one side and to the oxygen on the other side. We call this a degree 2 carbon. And then the third atom over here is the oxygen atom, and we call this a degree 1 because on one side it is connected to carbon and we are not counting the hydrogen. So we now start defining a first circle of this different structural groups in there, which happens to be the degree 1 carbon, the degree 2 carbon, and the degree 1 oxygen. Now the idea is you start with a reference atom. So initial circle is a circle of radius 0, so that's your reference atom itself. Having done that, we will expand it. Let's call it a circle of radius 1. And here what we will do is we will look at our nearest neighbor. After that, we have got a circle of radius 2, where we will start looking at the second nearest neighbor. So our first iteration, therefore, is going to be a circle of radius 1. So if I now think of my ethanol molecule as being written something like this, and I take this atom as my reference, and I make my circle of radius 1, then this atom only has one other atom in its neighborhood, which is connected by a single bond. So I am just going to write this as Cc. Similarly, if I take this atom as my reference atom, my circle of radius 1 starts looking like this. So I now have two different atoms in the neighborhood. Remember, we are not considering the hydrogens, and therefore one of those two atoms is a carbon, the other atom is an oxygen. And again, we just connect them by the bond, and so we have got a Cc and we have got a Co. So what we have now done is we have identified the direct neighbors and we have mapped out the edges. Similarly, one can also take this oxygen atom as a reference, and again you make a circle of radius 1. The only other atom it is connected to is the carbon atom, so you have got this oxygen carbon connected by the bond. Now, just like you did for radius 1, one will have to look into circle of radius 2 when you are coming to the second iteration. So if I look at a circle of radius 2, again let's write out the ethanol molecule like this. So circle of radius 2 means I am now looking at this region. So this is my reference initially. So circle of radius 2 means it is simply connected to a carbon, and then that one is connected to a oxygen. So I basically have a CCO. If I take this as the reference atom, it is going to be connected to a CO, and then unless you write the hydrogen, you won't actually have anything over here. So depending on how you want to do it, you can either write the hydrogen or you can eliminate it. If you are writing the hydrogen, then in addition to this path, one should also have this CCH type of path. But in practice, if we are not going to include the hydrogen, we need not actually have either of this denoted. Similarly, if you look at this oxygen as the reference and you are making a circle of radius 2, then you have this path from oxygen to the second carbon onto the first carbon. So you have got this OCC. And then if you go to a circle of radius 3, it is not going to make any sense because your molecule has already terminated. So if you now want to write down a resulting fingerprint, this fingerprint is going to be in form of sets of numbers. So each number can then correspond to the different atoms that we had initially identified. So you can see that I am writing it down in sets of 3 numbers. So one would be for a circle of radius 0, one would be for a circle of radius 1, one would be for a circle of radius 2. So what is really happening? We are writing down the results or descriptors of every iteration in the form of a string. Now this string will become the input for the hash function, and that hash function is going to result in a numeric output. So those numeric outputs are what we call this N1, N2, N3 for the first carbon, N4, N5, N6 for the second carbon, and so on. So all of these N values are going to be calculated from the hash function. And so that's how we use circular fingerprints. So I hope this is going to provide you with a reasonable introductory ideas on how molecular fingerprints can actually be used to decode the structure of a molecule. And once the structure of a molecule is decoded, once you have the structure-based feature vector ready, that feature vector can then be used inside your database, and you can actually go ahead and do your materials informatics with that structure-based feature vector. So with that, we will move to the next section in the next lecture, where we are going to talk about the mathematical description of the microstructure of materials. But until then, it's time for me to say goodbye and thank you.